Hi, in this video we're going to take a look at this Micsig DP750-100 high voltage differential probe for oscilloscopes. Micsig sent it to me directly and wanted me to do a review. My understanding is that this is a relatively new product. As usual, I will put a product link in the video description below for those who are interested. If you recall, I reviewed a Micsig DP100 series differential probe in one of my previous videos. That probe was a DP113, a 100 MHz bandwidth probe that can measure high voltage signals up to 1300 volts. I have used that probe many times since I reviewed it, and I can tell you having a differential probe when troubleshooting mains earth referenced live circuits is really essential, as otherwise you could easily short out the circuit if you are not careful and jeopardize your personal safety. It could also lead to extensive damages to the circuit under measurement, your probe, or even your expensive oscilloscope. Of course, you can always use a poor man's version of a differential probe by utilizing two channels of your oscilloscopes. And of course, in this case, you will just simply remove the ground clips and only use the tips of the probe for your measurements. Since each channel is inherently ground referenced, if you use the math function to subtract the signal obtained from one channel to the other, then you can obtain the differential signal. Of course, the obvious downside in this case is that the common mode rejection would be very poor, especially at high frequencies. So for this reason, you will need a proper differential probe for anything more than just casual measurements. Spec-wise, this high voltage probe is similar to that of the DP100-07 in the DP100 series. Both have a bandwidth of 100 MHz. The 100-07 measures up to 700 volts, which is comparable to the 750 maximum voltage this probe can measure. Other areas are also similar, but you can definitely see there are some improvements on this newer 750 version. For instance, the common mode rejection ratio, or the CMRR, is much improved for the DP750. Under low frequency, the CMRR is greater than 80 decibels, which is the same as the older DP1000 series. But as the frequency increases, there are some noticeable improvements. For instance, when the frequency is greater than 1 MHz, this new probe has a CMRR of greater than 60 decibels, whereas the 1000 series has a CMRR of just above 50 decibels. Of course, another noticeable difference is that the DP750 comes with a Micsig universal probe interface. So if you have a Micsig oscilloscope, the gain settings on this probe would be automatically recognized. But no need to worry if you don't have a Micsig oscilloscope. You can use the supplied adapter to convert this interface into a BNC interface. And the adapter is magnetically attached, so it's very convenient to use. Of course, you will then have to adjust the oscilloscope gains accordingly based on the selection on this probe. The accessories supplied with this probe is also very similar to those supplied with the DP100 series. They are these very high quality flexible grabbers and a couple of large alligator clips. Interestingly though, the default multimeter style probes are different than those found in the DP100 series. Let me grab the DP113 to do a quick comparison. So instead of utilizing a two-section design as we see in the DP100 series, this one on the DP750 are full-length probes with these removable tips. Now, this design is probably more secure as the tips snugly fit in the top here, and you wouldn't be able to yank this loose when you are using the probe here. But the downside is that once you put these tips in, you will need to pry them off, and sometimes you will need help with tweezers or a screwdriver before you can put another accessory on. Now, this one does come loose if you really pull hard, so I suppose you can just use your nails to pull these tips off. Now, while we have both of these probes out, I just want to quickly show you them side by side, and you can see that this new DP750 is definitely more streamlined, as everything is enclosed with the head of the connector here, whereas you do have this box for the DP113. Now, The buttons are slightly different. This one has 2 physical buttons. This one has one additional 0, but that's just because the range is actually done in this one button. Whereas for the DP113, we do have a 0 function. We can press these 2 buttons simultaneously while plugging in your power, and that's how you do the 0 calibration. So that's just the slight difference here. Okay, enough talking. Let's take a look at this probe in action. For the first test, I just connected the probe to a non-isolated variac, and the power of the probe is taken directly from the oscilloscope. And what I want to show you is when you boot up, when you actually first plug in this probe, it's defaulted to times 500, and you can press this button to switch between 50 and 500. By the sound of it, it seems like there is an internal relay to switch between these 2 ranges. Now let me power on the variac, and we can see the waveform on the oscilloscope. Now it's perfectly fine to see some of the distortions, as that's just a line quality coming in and has nothing to do with the oscilloscope or the probe itself. Right now the output voltage is set to be around 120 volts. Now let's take a look at the measurement. You will see that we're actually getting 58 volts, 59 volts instead of the 120, and that is because the probe attenuation on this scope, we can't really set it to 50, so we have to set it to 10, 100, or 1000. That's just a limitation of this oscilloscope. If you have an oscilloscope, you can actually set an arbitrary input attenuation, then you can get the correct reading on your oscilloscope. So that's just something you need to pay attention to when you're doing measurement. And now, of course, we can change the voltage, and we'll see that the waveform is changing accordingly. So this is just a quick demonstration of this probe in action. In this second experiment, what I'm showing you right now is the switching waveform of the driving MOSFET in a switching power supply. And you can see the waveform displayed on the oscilloscope. And we can take a look at the measurement and take a look to see the switching frequency here. So right now you can see the switching frequency is 58 kilohertz. Even though we're using a differential probe, you still need to follow all the safety precautions when dealing with this kind of high energy, high voltage circuitry. My advice is to always set it up first before you power on the circuit, so that you can make sure that you don't accidentally touch anything that you're not supposed to touch. Next, let's use this differential probe to measure a high frequency signal. Although this is a 100 MHz bandwidth probe, given the length of the probe wiring, it is not really suitable for dedicated high-frequency measurements. But given its bandwidth, we shouldn't have a problem acquiring a high-frequency signal. So let's take a look. Right now, what you're seeing on the oscilloscope is the output from the UTG-962E. Right now, we're outputting a 1 MHz signal with an amplitude of 10 volts peak to peak. Let me turn on the measurement display here so you can have a better look at what we're measuring here. So you can see that the frequency is showing as roughly 1 MHz, which is exactly what we're outputting, and the voltage is showing as 20 volts peak to peak, and that's because the attenuation of this scope cannot be set to the attenuation of what we're setting on this differential probe. Currently it's setting at 50 and our attenuation is at 100. That's why you see the discrepancy here. Anyway, so right now we're actually outputting a 10 volts peak to peak from this UTG-962E. And let me turn off the measurement, and we will increase the frequency. So the highest we can go is at 60 megahertz, and let's just zoom out a little bit, and let's take another measurement here. So you can see that the frequency is at 60 megahertz, and we don't really see any drop in that VPP here. Since I have both the DP750 and the DP113 here, I will just do a quick side-by-side comparison measuring the signal coming out from the HB8642B. Since the RF signal coming from the RF signal generator is very pure and low noise, we should be able to get some idea of how clean the measured signals are. Currently, the signal generator is outputting a 1 MHz signal, and both of the probes are set to time 50. And the input is set at 50 millivolts per division, as you can see on the scope here. You can observe that the measured signal from the DP750 is significantly cleaner than that coming from the DP113. This can be partially attributed to the improved specifications of the DP750, but of course, other factors are at play here as well. For instance, the cabling and some other environmental factors, but you get an idea of the improvements you are expected to see from using the DP750. I know I'll get questioned if I don't at least show you the signals at 100 MHz, but just wanted to warn you that it really is meaningless given the probes we're using here, as we cannot properly terminate signals at the probe's end. But let's give it a go nevertheless. Right now we're at 1 MHz and we can increase the signal. Right now we're approaching 100 MHz. So we're at 100 MHz and we can go beyond that. So let's see, right now we're at 140 MHz. Now let's actually take a look at the signal here. So we're way above the 100 MHz. You can see that we can still measure the signal. You can definitely use these probes to test the presence of signals up to and perhaps beyond the specified frequency bandwidth. Okay, that's pretty much all I wanted to cover in this video. If you liked the video, please remember to give it a big thumbs up and don't forget to subscribe to the channel for more videos like this in the future. I will catch up with you next time.